Share screen and share. Okay, folks. So let's look at Google Lynette. That's obviously by Google. They came up with something called the inception model. So it looks like this. It's applying convolutions, but in parallel. Applying, convolutions and pooling, but in parallel. So you have the previous layer. You apply 1 by 1 convolution, and then 3 by 3 convolution, 5 by 5 convolution, 3 by 3 maximum pooling, and then you concatenate the output of these guys into the input of that. Okay? Doesn't want to mean. Okay, never mind. So let's see how this looks like. So instead of applying filters in sequence, you apply ones in parallel and concatenate the outputs. Okay. So what is the problem with this? Is computational complexity. It's really, really expensive computationally. So it takes a lot of time to train. We'll understand why. We have so many convolutional operations. Yeah? Applying multiple of these operations in parallel, and that can take a lot of time.
Wouldn't the GPU help in this problem?
Yes, it helps a lot. So use same convolutions, i.e. you use the padding that preserves input width and height. We remember, right, the formula for defining the widths and height. And so I just adjust the padding so that it gives me same convolution. Meaning what? Meaning the input, the output is the same size as the input. So here, right, I have an input was, let's say from a previous layer was 28 by 28 by 256. I'm going to apply 1 by 1 convolution, 128 of them, 192 3 by 3 convolutions, 96 5 by 5 convolutions, and 3 by 3 pooling. Yeah, pooling would be the same width as the like it's a single width. Yeah, okay. What is the output size of the 1 by 1 convolution with 128 filters? Remember that I want, right, same convolution. So I want the size of the output to be exactly the same as the input. So what is the output size of the 1 by 1 convolution here? I don't know the padding, I don't know the stride, but I know that, right, I want to set these guys so that I preserve the input widths and height. So what is the input widths and height? 28 by 28. What do I want the output here to be? I want it to be the same. So I want it to be 28 by 28. Yeah, regardless of the padding. And so I set these other things so that I get 28 by 28. So I have 28 by 28. Why times 128? Because that's the number of filters. That's the depth. What about this one? 3 by 3 convolution and 192. Again, it's the same convolution. So I want the output size to be 28 by 28. Right, so I have 28 by 28 by 192. This one is 28 by 28 by 96. So I set the padding so that, right, if I do 28 minus 5 plus 2 times the padding plus 1, right, this gives me 28. So I figured out what is the right path. So it gets me 28 by 28 by 96. This gives me 28 by 28 by 256. Okay? Why 256? Because it's the same size depth as the input, because it's a pooling layer. So how many convolution? What is the output size after filter concatenation? Who can tell me what is the output size if I do filter concatenation now? What does mean filter concatenation? I concatenate the outputs like this. All of these guys, I concatenate them into one image. It's 28 by 28 by 128 plus 192 plus 96 plus 256. Yeah? So 28 by 28 by 672. So how many convolutional operations do I have? Yeah, this is what tells me why is it computationally expensive. I have 28 by 28 by 128. That's the number of weights here, times the 1 by 1 by 256. Why 1 by 1 by 256? Because it's a 1 by 1 convolution. Yeah, so it's 28 by 28 by 128. That's the number of, right, basically 1 by 1 by 256 convolution operations that I have to do. And remember, the convolution is a cube, or it extends to the depth of the input. So I have these guys, and then I have 28 times 28 times 128 of them. So that's the number of operations for this guy. For the second guy, it's 28 by 28 by 192 times 3 by 3 times 256. So that's the size of the input. And for this one, it's 28 by 28 by 96 times 5 by 5 by 256. Okay. Again, because I wanna, it extends to the depths of the network. So a total of 854 million operations. Imagine in just one layer, it's 854 million operations. Right? So this is really expensive. That's why it takes a lot of time to train. Okay. The pooling, of course, is just maximum pooling, so it's not as expensive. This involves multiplication and addition and so on, so it's really expensive. So it's very expensive compute. Then notice that the pooling layer also preserves the feature depths, so it preserves 256, and so you end up really with extended, right? After the filter concatenation, you extend the size. So the size only grows after every layer, rather than it doesn't decrease. So it either stays the same or grows after every layer, because you have at least 256 here. The depth is at least 256 plus the number of filters from the convolutions. Okay. Right. So you're gonna do what? You're gonna use filter, use 1 by 1 convolutions to reduce feature depths. Okay, so this is what they use in the Google Linnet model. Okay, well, in the inception model. This is how it looks like. They're gonna use, right, on the left. This is what the original inception module, and this is the one that is currently used. So you basically apply 1 by 1 convolutions before passing it to the other convolutions. And 1 by 1 would help reduce the depths. So let's see how. Okay, so I apply 1 by 1 convolution, 64 of them. That gives me, again, it's the same convolutions, meaning the output size will be exactly the same as the input size. So I get 28 by 28 by 64 because I'm applying 64 of these. And I get 28 by 28 by 64 because I'm applying 64 of these. And then I have 3 by 3 pooling. I get 28 by 28 by 256 because it's a pooling layer. Okay, so I have these guys, and then pass these as input to the previous, right, set of convolutions that we've discussed in the previous slide. Okay. Now this reduces the number of convolution operations that I do from 854 to 385 operations. Why? Because I've reduced the depths here by doing 1 by 1 convolutions. I reduced the depth to 64 from 256. I reduced the depth to 64 from 256, and here I have the same depths as before. Okay, so I end up with really reduced depths compared to previous one. Yeah. I'm sorry. Can you repeat, Hamza?
Still, 358 operations is still a huge number. It's not that better.
Yeah, not that better, but it's much better than, right? You reduced it by the 1/3, but still a lot. It's one of the most extensive neural networks out there. So I think they trained it in their paper. They said they trained it for a month. So it actually took a month to train.
And what if at the end it was not good? Like this whole month will be for nothing?
So they're looking at, of course, they look at the curves. They look at they're observing the training error. They see that it's decreasing and so on. So they stopped it. They were running multiple of them at the same time, and they were, stopping some of them and killing them because they were not performing well, and keeping others because they seem to be, the error keeps decreasing as they train more and more. So it's like a process of observation, yeah. But
Sir, so like, can they see it like like dynamically while it's training? Like usually in our assignments, we see the error and the curve after it finishes.
You can always output, right? As you're training, output the values, draw the curve as you train.
Oh, okay.
Yeah.
Yeah. Thank you.
You're welcome. Okay. So this is how the network looks like, the overall network. It's a very complex network, yeah? You can see you have some regular layers, and then you have these inception modules, I'm sorry. And then it's stacked on top of each other, and then you have fully connected layers at the end. So similar to any one of the CNNs we looked at. Okay. So they had 22 total layers with weights, including each parallel layer and an inception module. This is the full Google Linnet architecture. You can also download it, as I told you, download the architecture, download the weights, and use it in your project. Okay. So this is was a quick introduction. I want you to know the names of these guys. You don't have to know the details of them, but know the names of these guys and know that they're out there and you could use them in your on your data. Yeah? So basically, you don't have to go every time you're training a CNN to train it from scratch. You can use these models that are already pre-trained and apply it on your data. How do we do this? There are two techniques for doing this. Data augmentation and transfer learning. These are very important practical aspects of deep learning. So data augmentation means the following. It's a means of gaining more training data and to overcome overfitting. Because these networks involve a lot of parameters, as we've seen, and they're very deep, we need a lot of training data. And most likely you wouldn't have a lot of training data. So you'd have some data, not very little, but it's not that it's a lot, yeah? And so one way of augmenting your data is to do data augmentation. So data augmentation is a very simple technique. It involves the following. You take your images, you do some horizontal flips on them. Yeah, so here's an image. You say, okay, I'm gonna flip it horizontally. I'm gonna do some cropping, random cropping and scaling. And this will give me additional images. So this image became two images, right? If I do horizontal flip, or I do vertical flip, or I do, rotate it with some angle, that gives me additional images in the training data. Then I do a cropping and then scaling, that gives me additional images, yeah? And I keep doing this. So random contrast, brightness, I change the brightness, I change the coloring, do some filters on them, and I get more and more and more images of the same instance. So I take the same instance and transfer it into, let's say, 5 or 6 or 10 different images, yeah, and use this as training. That's pretty much it. Yeah, that's what is data augmentation is. Any question about it? So it's a very important technique to avoid overfitting in convolutional neural networks. And we, again, right in this project the current project that I'm working on, this is one of the things we immediately did. Yeah, because we didn't have enough training data. We went and just augmented the data by doing some horizontal flips and some, random cropping and so on. Yeah? Good. Transfer learning. What is transfer learning? So typically it's again for regarding the issue of large training data. So you need a lot of data if you want to train or use CNNs. That's something that is, it's a fact, yeah, because they involve a lot of parameters. Okay. So transfer learning means the following. Means I take a model that is already trained with its weights. So let's say this is, I think, maybe AlexNet or something like this. Or no, it's just one model, yeah, a CNN that is already trained, that it has some weights. And what I do is, depending on the size of the data set that I have, I either train only the fully connected layer at the end. So let's say it looks like this. This is the model that I downloaded with its weights. I'm gonna freeze the weights of all of these layers and just train the final layer, the final fully connected layer. Only train this one. Meaning what? Meaning I'm gonna update the weights of this layer only, and the rest of the weights stay exactly the same. Yeah. So reinitialize this and train. Basically reinitialize the weights here and train the network, just updating the weights of this layer. So in the back propagation, you're just updating the weights here. These remain the same in every iteration. Okay. If I have a bigger data set, I can afford to train maybe all the fully connected layers, or even depending on how big the data set is, I can train a little bit of the convolutional layers. And the more data I have, I can afford to train more layers. But the idea is to really kind of take a pre-trained model and then freeze the weights and then just apply, apply it on your data set and train the final layers. Yeah? The most important thing is to train the final layers. Of course, you'd have to adjust the final layer because the final layer might have 1,000 classes. So if it's trained on ImageNet, then it will have 1,000 classes, but maybe your data set has only 2 classes, 3 classes. So you have to change the final layer architecture and just train it on, on your new data set, freezing the weights of the original layer. Yeah, and this works brilliantly in practice. So again, this is exactly what we did in our project as well. We just took MobileNet, I think, and VGG19. We froze the weights and just did transfer learning on our data set, which was a binary classifier. Yeah, and it worked really, really well. So we had an accuracy of over 90%. Okay, that's pretty much it when it comes to convolutional neural networks. You have an assignment on it, so I already posted the assignment. Not very complicated. If you've done already the assignment on neural networks, you should be able to do the one on CNN very easily. And we're going to talk next about recurrent neural networks. So recurrent neural networks are a little bit tricky. So I hope that you try to read and finish reviewing the material on CNN so we can put it behind us and start with recurrent neural networks. Recurrent neural networks is used more for text classification and natural language processing, so not computer vision. Yeah. Any questions? Okay, then we'll stop here and we'll talk on Thursday. I'll post the links to the recordings as usual. Okay, folks?
Thank
you. Yeah. Yeah.
Okay, thank you, sir.
Yeah, good luck, guys. See you. Stop share. Stop recording.